Okay, the stability of the radical. Well, similar to the carbocation. If you still remember carbocation, right? Tertiary carbocation is the most stable compared to secondary and primary. And that's because of the hyperconjugation. It's been a minute since you learned hyperconjugation. Let's review it real quick, all right? So hyperconjugation down here. So it's a stabilization of an MDP orbital. So carbocation have an MDP orbital, which is really, really unstable. It's not, this carbon is not octet. Right? So it needs someone to help them stabilize it. Really unstable, really lonely. Well, who can help them? The neighboring CH bond. If there's a CH bond nearby, adjacent to it or next to it, so this CH bond right here, there's a lot of electron density compared to an MDP orbital. There's nothing on here, right? There's electrons right here. So CH bond say, well, don't worry, I have a lot of electrons, so I'm going to share some to you. Stabilize it carbocation a little, just a little, right? And the more CH bond, the more hyperconjugation, the more stable the carbocation. Well, the radical is electron deficient species, right? If this were to be a radical, so 1 electron in here, this carbon can have only 7 electrons. Does it make sense? So 1, 2, 3, 4, 5, 6. This is carbocation, 6 electrons. If this were to be a radical, 1 dot right there, 1 electron, so 7 electrons. It's still electron deficient species. Stabilization by hyperconjugation also applies. All right. Let's take a look right here. So I'm going to make all of them a radical. I have a methyl radical, a primary radical, secondary radical. All right. And methyl radical, you will never see the methyl radical. It means little, not a lot, because it's not as stable. There's nothing stabilize it just by itself, right? 7 carbon electrons, not that stable. Primary radical got a little hyperconjugation right here. So this CH3 group right here, a CH bond can stabilize that radical by sharing the 2 electrons right here. All right. And you can guess that the secondary have more than 1 CH bond stabilize that radical. And tertiary, you don't have to guess, a lot more CH bond, a lot more degree of hyperconjugation. All right. Now, and here's what happened when so compare with all the radicals that you have seen so far, the tertiary is the most stable, right? And the methyl radical is the least stable. And there's no doubt, this CH bond is never one to break. If you want to break this methyl CH bond, it will cost you 435 kilojoules per mole, compared to an ethyl, which is going to make a primary radical, which is more stable than the methyl radical. It doesn't need that much energy compared to the methyl. Okay, and secondary carbon, which is going to make the secondary radical, which is even more stable than primary. The energy that costs to break this bond is less, only 394 kilojoules per mole. And tertiary, you can guess the trend. You see the trend there, even lower, 381 kilojoules per mole. Let's look at something more stable, even more stable than the tertiary. Down here, right? We got allylic and benzylic radical right here, right? Because of the resonance structure, you can draw resonance right here with a double bond. And this guy have even more resonance structures, can resonate to the ring. All right. So these 2 type of radicals, we call allylic radical, a benzylic radical. They are even more stable than tertiary. And guess what? CH bond right here is easier to break, even easier. Only 364 kilojoules per mole or 356 kilojoules per mole. Okay, because the radical right here can be shared with all the 3 carbons here. This radical can be shared with all 7 carbons total in here. All right. Now let's look at something really, really unstable to the extreme. I go back to the top there. Even worse than methyl radical or primary radical, the vinylic radical. Nothing stabilizes it by itself, right? So to break CH bond here, it takes a lot of energy, 464 kilojoules per mole. All right, this guy is worse. It's the worst. All right, if I ask you to rank, all right, so the stability of these radicals, what do? Pause the video, do it by yourself, and then check with me. What we got? So A, the secondary, right? B, a secondary radical. C, oh, this one is good, tertiary radical. D, the primary radical. E is also secondary, and F is also secondary. All right. Now I'm going to rearrange it. So the tertiary is the best one. Primary should be the worst one. So, and I'm going to group the secondary together. So look like that. All right. These are all secondary in the middle. Tertiary is the best one and primary is the worst. Okay. And look at the tertiary one real quick. This guy is even better because it got resonance stabilized with the double bond, right? Just like in A, which is secondary, like the other three. But this guy got resonance stabilized with the double bond. I show you how to draw the resonance structure. So right there, break the pi bond from double bond on the right. The other electron on here will go to the carbon on the left side, right there. And in A, you can do the same thing as well. From double bond right here, break this pi bond. All right. So C and A, so the stability should go from C and then A and then all the secondary and all the primary. All right. But one thing though, do you realize what's going on with this, guys? This guy right here. It is secondary, but it's on a vinylic carbon. And this guy is the worst, right? Nothing stabilized not lone pair, the radical. Right? So I'm going to put E after D. Move that over there. Move it right there. Right? This is even worse. Okay, so the rank going to go to C, A, B, and F as equal in the stability. D primary, and then vinylic is the worst. Okay. All right. Another way that I can ask the same question. Where is the weakest bond for a radical process? Right. So anything that a CH bond that when it breaks, it forms a stable. So say one more time. No. A CH bond. That when it breaks and it forms stable radical, that's an easy bond to break, which is right here. This is allylic position. If you put a radical right there, you're going to have a resonance. I'll take a look real quick. So you can have a resonance structure there, like that. So this is resonance stabilized radical. This CH bond is easy to break, easier than the vinylic CH bond down right here. Just a methyl group right down here, all right, or even tertiary. Okay, this guy is the best one. If you see the resonance. All right. Chapter 10, class activity 1. We have 3 questions, and this is the key. All right, you know what to do with it.